Today I'm going to introduce the concept of recursion. It's a tricky concept, but a useful one in computer science. And I'm going to give you a basic definition, but then we'll look at some examples because I think this is best understood by seeing it in action. Basically, a recursive function or method is one that solves a problem by calling itself. So let's take a look at how that could work. I'm going to create a simple program that calculates the value of bases raised to exponents, so mathematical powers. In Java, there's no power operator like multiplication or addition. In some languages, if I wanted to raise 6 to the power 5, for example, I would do this. And this little symbol here is called a caret. And that's spelled C-A-R-E-T. And in some languages, that functions as the power operator. Java has a math class that has the ability to calculate powers using a method called pow. And you can pass in the base and the exponent that you want to raise it to. So what we're going to do is look at how we can model this. So we'll make our own methods to do this. First we'll do it using a loop, and then we'll do it recursively. So I'm going to create an iterative power method called ipow. And this method is going to take two parameters, one of which is the base that I want to raise, and the second one is the exponent that I want to raise that base to. So if I think about doing this iteratively, or looping, which is what the I stands for, to solve this problem, I would use some code, something like this. So the comments clarify here that this method is only valid for bases that are greater than 0 and exponents greater than or equal to 0. All I'm doing is starting off with a value of 1 and then multiplying that 1 times the base as many times as is indicated by the exponent. So a really simple looping program. Let's take a look at how that would work. And since I'm calling this method inside of a class's main method, not creating any objects, I need this method to be static as well. Okay, so that is the correct answer. And we now have our iterative solution to calculate a power. What would it look like if we solved this same problem recursively? Whenever you're trying to generate a recursive solution to a problem, what you want to do is break the overall problem into smaller versions of itself. So if we think about what a power is, it's some number multiplied by itself a bunch of times. So let's take a look at how we can think about calculating a power that way. A really simple way to think about this is if I was trying to raise 6 to the power 5, I know that that's the same as 6 times 6 5 times. 6 to the power 4 is the same as 6 times 6 4 times. So this expression here is the same as 6 to the power 4. If I look at this in comparison to 6 to the power 5, I can see that what I'm really doing is multiplying 6 to the power 4 times one more 6. So if I want to think about 6 to the power 5 as a slightly simpler version of itself, I can think of it as 6 to the power 4 times one more 6. So a recursive idea of solving this is that a power can be calculated by multiplying a slightly smaller power times the base. And so since I'm calculating a power here as part of solving a larger power, this is a recursive way of thinking of the problem. I'm using the power method as part of my solution. So if I think about a general case, if I have some number n raised to the power 5, that's going to be equal to n to the power 4 times n. And if I want to generalize this even more, let's say I have some n that's raised to some other exponent e. That's now going to be equal to n to the exponent e minus 1 times n. This is the tricky step. This is the recursive idea here. I subtract 1 from my original exponent, and that makes my power get slightly simpler. Eventually, if we look at this, the idea is that eventually this exponent is going to become 1. And when the exponent is 1, we know that the answer is going to be n. Just like if I had 6 to the exponent 1, I know that that's going to be 6. So if you look at this situation here, there's no recursion happening. When I'm calculating a power that's raised to the exponent 1, the answer requires no recursion. Similarly down here, if I'm calculating any value n raised to the power 1, I know that the answer is going to be n, and it's going to require no recursion. These situations where we know what the outcome is going to be based on the value of one of the parameters, these are called base cases. So a base case is a recursive scenario that requires no recursion to get the solution. And you'll see what that looks like in a second. So if I'm solving this algorithm here, first I'm going to create my base case. That's the way you should always start your recursive algorithms. If my exponent is 1, I know that all I'm returning is the base. Because no matter what this base value is, any base value raised to the exponent 1 is the base. This is my base case. And don't confuse this word base in recursion with the exponent idea of the base that you're raising. If that's not the case, I'm going to return the base times that same base raised to a slightly smaller power. And that's it. That's my recursive solution to calculating a power given some base and some exponent. So let's test it out. If I go up here and change this to an R, let's try running the recursive power of 6, 5. And this should be 7,776. There you go. So it's a different way of solving the same problem. And if you look at the code, we might say that the recursive solution is a little more elegant. One simple comparison, that we can return a value or we can return another value, the second value being recursive, and it calls itself again with slightly different values. In this case, we just decrement or decrease the exponent by 1. This iterative solution, it's still pretty simple, but you need to take a look at it to really figure out what it's doing. And so it's slightly less elegant to read, but it still works just fine. So some key takeaways here. A recursive method is one that calls itself to solve the problem. Every recursive method requires a base case, and if you're not sure why that is the case, Think about what would happen if we didn't have a base case. Remember, the base case does not have any recursive component to the answer. If we didn't have a base case, it would mean that every answer had a recursive case, so every single answer would involve some part that called itself again, called itself again. So we'd have infinite recursion. So everything must have a base case, and your recursive cases, that's what this is called, your recursive cases should be changing your result in such a way that it's approaching the base case, right? So this is always getting closer and closer and closer to being done, which means getting this result with an exponent of 1, returning a non-recursive answer, and jumping out of the method and being finished. So recursive methods call themselves to solve the problem. Every recursive method must have a base case, at least one, sometimes you'll see more than one, must have at least one base case and at least one recursive case. We'll look at pros and cons of recursive methods a little later on, and we'll look at more examples as well, but that's a basic intro to the idea of recursion. Now, if you're a little confused about this whole concept of recursion, you're in good company. It's a difficult concept to understand. It's one of the big things you have to level up on to become a good programmer. And even the folks at places like Google realize how difficult it is. If you search on Google for the term recursion, they have a did you mean function here that corrects you to see if you maybe mistyped it. But here they suggest that if you're looking up recursion, you might want to look up recursion. And so that's their inside geek joke. And also the folks over at Think Geek that sell lots of geeky stuff have a t-shirt that says, in order to understand recursion, one must first understand recursion. So this is not an easy concept, but once you get it, it winds up really helping you solve some programming problems that are a little tricky to solve in an iterative or looping way.